Alright, this is our notes for 2.4. The homework has 2.3 and 2.4 mixed, but they are two separate sections. This is the last section that we cover in Chapter 2. It's statistical graphs other than the histogram, and some of these are very basic that you'll seen before. Alright, so the first one that we discuss in here is a frequency polygon. This is important because we're going to go a little bit further with our discussion of what we do with these histograms and these things that we make. We're using statistical data, these data from samples, to give us information about the population and talk about the shape of a graph. So basically what a frequency polygon does here, if I take a histogram and I put that histogram, or sorry, if I make the histogram and I go basically, if you notice these dots are right in the center of the histogram bars. If I go one more distance out on both ends, the same distance that goes from the middle of the bar to the middle of the bar, if I go one more of those to the left and one more of those to the right and just connect the center of the bars in the middle, then I've created a frequency polygon. Okay, so this frequency polygon is basically just connecting the tops of the histogram that we've created and giving us the shape of the distribution. Okay, we use these curves to mimic the shape of the population. So we'll talk about this more in detail later on in the coming chapters. But we're going to start finding areas under these curves, okay? And the histogram gives us the shape that we're after, okay? A lot of the times the histograms we're going to see are bell-shaped, symmetric data. This one's obviously not symmetric. It's got a nice little tail going on over here to the right. Okay, so that's a frequency polygon. It's basically a kind of a drawing on the outside of a histogram. All right, and then here are relative frequency polygons, same thing. Except again the scaling on the side is relative frequency versus frequency. Alright, notice that this is a double one. They have one for the men data set and the women's data set, the stuff we've been talking about before here in the previous videos. So there was two data sets originally. Anyway, they're putting the men on one frequency polygon and the women on another to show the difference between the two. So we're seeing that the men peak, so a mode occurs here at a lower pulse rate than women. So it's showing that women's pulse rates tend to be a little bit higher, is what we're seeing from this dual frequency polygon here. Alright, some other ones that we see. This is an ogive or an ogive. Some people pronounce it that way. But what an ogive is it's basically a frequency polygon for a cumulative frequency. So if we take, this is something we saw in our last slides. Remember, we got the cumulative frequency from adding these numbers together. So this 26 comes from 12 plus 14. 37 comes from 12 plus 14 plus 11. 38, 12 plus 14 plus 11 plus 1, and so on all the way down. And that's what this is a plot of. Alright, this goes up to 12, this goes up to the 26, the 38, alright, and so on and so on and so on. So this is a plot of cumulative frequencies and or relative frequencies. Dot plot, very popular tool. So each dot represents a measurement that took place. So if we took our pulse rate data and put dots over the common pulse rates, so there was 1, 2, 3 people that had a pulse rate of 60. 1, 2, 3, 4 had a pulse rate of 64. So each dot represents a measurement. Now, if there was a key over here and it said each dot represented, 2 measurements or 10 measurements, you could adjust the scaling that way. But most of the time, each dot represents one value, and they're all giving you the same information. All these are showing you where the data fell and the shape of your distribution. Alright, and then a Stemplot. So if you look at this data set that we have here, there's a 6 here, and these stems are like the tens place in this case. Sometimes it's the ones place and the leaves are decimals, like the tenths. But it's always the stems are one place value and the leaves are the next place value beside that. So this 6 means that in our data set there were some values that were in the 6 times 10, 60 range. So that were measured in the 60s. The leaves represent those individual measurements. So this 6 and this 0, what this over here is saying is this 6 and this 0 correspond to this 60. Okay? That 6 and that 0 correspond to that 60. Right? That 6 and that 0 correspond to that 60. Right? And then that 4 right there corresponds to 64, etc., etc., etc. Okay, so that's each data value actually shows up in this. And then if you bring in a histogram of the same, this is pulse rates for females, so is this. If you take this thing and you rotate it, alright, then maybe if we scaled it down a little, you see that it fits right on top of this data. So it's basically, again, just like a histogram that's been rotated to still mimic the distribution of your data. It's just doing it a different way. The nice thing about a stem plot is it's giving you the same information that a histogram gives you. It's just you can see the data as well. Okay, with a histogram, you know that yeah, there's 12 values that fell between these two numbers, but you don't know what the values are. They could have all been 60, they could have all been 68, and it would have still fallen in that that bar, which makes a big difference as far as the mean and all that stuff goes. But with a stem plot, you can actually see what the data is along with what the distribution is. But again, you just have to rotate, adjust, and see your values to kind of view it as a histogram. Alright, and then obviously bar charts. Everybody's familiar with bar charts. So this is a double bar chart. When you see that, usually we're making a comparison of multiple things for different time periods. Alright, so this is showing median income for males and females, different years. The blues represent the males, the reds represent the females. Alright, and then if your frequencies decrease from left to right, so meaning your first bar is your highest down to the last bar is your lowest, that's what we call a Pareto chart. So it has to have that order to it to be considered Pareto, otherwise it's just a bar graph. Alright, and then a pie chart. Everybody's seen one of these before. The areas of the sectors, the wedges, whatever you want to call them, they represent the heights of the bars in a bar graph. But basically they're telling you the same information, just using sectors rather than bars to display that information. Alright, and then something that we're going to discuss in much more detail later on, a scatter plot. This is when you have bivariate data, so you have two variables going on at the same time, and each dot represents two measurements. So this dot right here represents a chirp rate somewhere between 1,000 and 1,050. It looks like around maybe 1,040, and a temperature between 80 and 85, or maybe around 83. So 1,040 chirps per minute, 83 degrees is what that dot represents. Alright, so it's like we measured two variables at the same time and displayed them all together to show that there's a relationship possibly between the two variables. Alright, the last thing we're going to talk about in Chapter 2, a time series display. Time series graph, I wrote over here, think stock market. That's something that we see a lot from day to day. There's apps on your phones that display the stock market. Usually they show it a couple times during a newscast, but they depict that horizontal axis needs to be some unit at a time, and it's showing change over time as time progresses. So you see these a lot in higher level maths as well when you're doing modeling and everything. Alright, that's the end of Chapter 2. All these videos in Chapter 2 are what your test material is going to be on and what your homework is on this week. So again, if you see anything that you have concern about, just send me an email.